So today I'll be discussing on mmSpoof, a resilient way to spoof millimeter wave radars. This work is a collaboration from UCSD, advised by Professor Dinesh Bharadia, and Professor Aanjhan Ranganathan from Northeastern University. So millimeter wave radars are almost used in every cars right now, what we have been seeing. In general, they'll be enabling key features such as adaptive cruise control or emergency braking. Say, adaptive cruise control helps you to maintain a safer distance while driving on a highway, and emergency braking helps you to determine possible collisions by estimating the distance and velocity of the vehicle in front of you, and applies brake if it is really necessary. And it enables many other features. However, are these really secure enough? We try to address this question. So imagine driving on a highway where the radars estimate distance and velocity of the front vehicle for safe driving. Now, if there is an attacker in the front vehicle, when he turns on spoofing, a phantom car appears in the radar view. The radar now estimates the distance and velocity of the phantom car instead of true values. This manipulation of radar measurements with a desired quantity is what we call spoofing. This leads to a phantom brake and may potentially lead to a severe accident from the car behind us. These attacks are highly effective, mainly because of their ability to spoof both distance and velocity. In our attack model, we assume that the victim vehicles are equipped with millimeter wave radars. They transmit radio waves and measures distance and velocity based on the reflections. And there is an attacker in the victim or the vehicle in the front, and he, like with a spoofing device, he'll try to spoof both distance and velocity at the radar. To achieve this, existing attacks transmitted active custom waves that mimics the radar waveform and tries to spoof it. But this requires active transmission. Additionally, they need a tight synchronization between attacker and victim. They even used wired synchronization to achieve this. In reality, in a wireless scenario, achieving this synchronization is not feasible. We propose mmSpoof, a robust spoofing attack against millimeter wave radars using reflect array. In our attack, we use reflect array where it measures, it captures the incident radar wave and adds a frequency shift on top of it. That will kind of create both spoofing in distance and velocity. Since we only rely on an incident wave and modify that reflection, we don't need any active transmission of custom chirps. Additionally, the reflection-based model allows us to eliminate the need for synchronization. Further in this talk, I'll discuss these three key contributions in mmSpoof. First is how we enable independent distance and velocity spoofing. And then we show a prototype with just commercial available hardware without any new custom hardware. And finally, we show how we can do real-time radar parameter estimation. Before going into how we can estimate the distance or spoof the distance, let's see how the existing radars do or estimate the distance. They transmit FMCW chirps, or these chirps kind of have an up ramp where it varies the frequency from its minimum to maximum value, followed by a stop time. It receives back the reflections, and based on the transmitted signal and received reflections, it measures distance and velocity. We know that distance can be measured by speed into the time difference. FMCW radars measures frequency difference. This will manifest as time difference because of the linear relationship and used to detect distance. Now, mmSpoof sends a modified signal back to the radar and spoofs distance. With this, one naive way to do is maybe introduce delays. That delays will help you to change the time difference and create a change in the corresponding distance measurement. But positive delays can increase the distance. However, we cannot create negative delays. That will limit the system's ability and failure to spoof shorter distances. On the contrary, we propose we exploit the frequency relation between a frequency time relation of FMCW, where we induce frequency shift on the reflected signal. This will manifest as time difference at the radar and change the corresponding distance. So by applying a positive frequency shift, that will reduce the frequency difference and manipulates your time difference measured at radar, thus changing your effective distance. Similarly, by applying a negative shift, increase your distance. So applying a frequency shift at reflect array, you can spoof your distance at radar. Now let's see about the velocity. Unlike distance, for velocity, you need like multiple chairs because it measures distance over time. To estimate velocity, they radars kind of use a phase change with time. Or also, we also know it as Doppler frequency. We measure it as like total phase difference by total time taken. And now, the same frequency shift at radar, reflect array, changes the Doppler frequency at radar 2. It also changes your Doppler frequency, thus affecting your velocity. So one thing to observe here is, it's great that a single knob frequency shift is changing both your distance and velocity, but did it solve our problem? It actually added one more challenge, that it is coupling the distance and velocity spoofing. Say how it goes. So if you are increasing frequency shift, your distance increases linearly, but your velocity increases from 0 to, spoofed velocity increases from 0 to a maximum value, then it again jumps to your minimum value and again increases back to 0. This pattern repeats with your frequency shift. Now say if we wanted to spoof a distance d change, we need to apply corresponding frequency shift f shift. But applying this frequency shift also creates some unwanted random change in the velocity. We call this as coupling. How do we solve this coupling issue? One naive way to do is maybe synchronize at a chirp level and compensate in every chirp. But this will again require you to have a higher synchronization and make your model infeasible. So we kind of rely on two key observations. First, the periodicity in velocity spoofing. If we apply frequency shift in multiples of f sharp, only distance changed while keeping your velocity constant. Thus, applying your frequency shift in multiples of f sharp, you can only change distance. And the second property is, if we change frequency less than your f sharp or the periodicity, you see your velocity change from your maximum to minimum, but your distance like hardly changing like a few centimeters. So by applying a smaller frequency values, you can only change velocity. In general, to independently spoof both distance and velocity, we need to apply frequency shift in steps to spoof distance and smaller frequency values to spoof velocity. Now we know how we can create frequency shift, but how do we create in the actual hardware? We show that we can create this entire prototype with just like COTS available hardware. We have three components: one transmit phased array, received phased array, and SDR. First, the received phased array captures the transmit radar signal. It downconverts it and sends to both SDR and the transmit phased array. The SDR do parameter estimation on top of the downconverted signal and creates a frequency shift. This frequency shift is applied on the transmit clock and then later given as input to a transmit phased array. The transmit phased array kind of transmits the data back to the radar at the corresponding desired frequency shift. What we are actually doing here is just receive at center frequency ST, but instead of transmitting the same frequency, transmit at FC plus F shift. This additional F shift will spoof both your distance and velocity. So we show that entire prototype can be built with two COTS available phased arrays and SDR. Anyone can build this attack and do spoofing on the go. So now we know the F shift. How we actually design the frequency shift is, you also need certain parameters about the radar. Unlike the existing works, we do this estimation in real time. So we kind of first measure the measure the energy levels in your or power levels in your frequency domain and estimate the corresponding start frequency. Once you have the start frequency, we then measure the spectrogram around that start frequency and extract chirps. From the extracted chirps, if we sum your energy levels in your frequency domain, you'll get an energy profile. The periodicity in this energy profile will help you determine the chirp time. Later, from this chirp time, you can extract one single chirp and estimate corresponding slope. These parameters are enough to get your desired frequency shift and spoof your desired velocity and distance. So we showed this attack in real scenarios. First, we thought how the actual radar estimate distance and velocity in real time. Say if there is a car stopping in front of the radar, what we see is the distance will be exponentially decreasing to 0, and velocity drops to a minimum value, and later increases again to 0. So our question is, can we spoof this attack with our model, or mimic this exact scenario with our model? For this, we showed in two scenarios. First is with no relative velocity, or the static scenario, and the other is with relative velocity. In the static scenario, we placed that our reflect array with two phase arrays and SDR on the car, and placed radar at a distance varying from 30 meters to 100 meters. Now with this scenario, we observed that when the true distance is always 30 meters, we linearly or exponentially decrease the distance for the radar distance, and for velocity, it drops to a certain value and again increases back to 0, exactly mimicking the braking pattern. This will actually fail your emergency braking feature. In the other case, in the relative velocity scenario, we kind of kept this radar onto the car and placed our reflector stationary within a certain distance, while moving the moving car, while there is a relative velocity between the moving car and the stationary device. We also measured the distance and velocity through LiDAR to maintain it as a ground truth. While the ground truth moves from 50 to 100 meters, the estimated distance on the radar moves from your 80 meters to 130 meters, adding an additional 30-meter shift. In addition, what we see in velocity is a 3 meter per second additional spoof. This will actually break your ADAS or adaptive cruise control. So in general, all the existing works hardly meets like 1 or 2 of these requirements and easily be detectable. In contrast, we show that mmSpoof meet all the requirements and has been demonstrated as a strong and robust attack. Though mmSpoof, despite mmSpoof has strong counter, or have a robust attack thing, it still has few countermeasures. First, employing a high-resolution radar, where you kind of get multiple reflection points and able to extract the original distance and velocity. And the next is using multi-sensor fusion. Even one of your sensor might fail. Other sensors will help you to detect the true values. Finally, by changing victim chirp parameters in every chirp, that way it will outdate your parameter estimation, and in general, as a result, it will invalidate your overall attack. For more details, please refer to our paper or visit our website. Happy to take any questions.
Questions?
Yeah, it's really interesting work. Is there any way to make the car appear further away or disappear, or will the physical reflection always dominate?
Okay, so here we show 2 things. Like the original car will also appear here, but we also show a phantom car in front of the radar. So it kind of sees both. Alternatively, we are still working whether you can completely remove the existing car. You can also spoof later. So instead of the phantom car just before the car, if you see the moving scenario, we see the phantom car is away from the original car. So we can do both, like before or after the original car.
A follow-up question. Yeah. So you want the attacker wants the car to disappear?
Not in this way.
The follow-up that you just mentioned.
Yeah, you can probably do that, but I think existing work is not working.
What was the incentive of the attacker, like disappearing? Like they will get hit, right?
Yes, that's that's what we are showing. It's like radars are not fully foolproof. So you can like follow the countermeasures, and that will like solve the flash.
Okay. Yeah. Other questions?
Just to highlight again, these radars are like heavily used even in the current cars, so we had to be like secure enough.
Okay. Thank you.
Yeah, thank you.